Today we're going to see how the logarithm and the base 10 exponential apply to each other to be inverses. And we'll look at how they can be used as inverse operations. So behind me here I have written again for us the logarithm with a base 10 exponential. We refer to this as the common logarithm. And if you're using a calculator, you'll see that this base 10 logarithm shows up as log without the base 10. All right, so from here on out I will refer to the base 10 common logarithm as just log. So this log right now, this problem I'm looking at here is saying find the log of 100,000. Well, last time we were together, we talked about how the logarithm came about from this expression, 10 raised to the power of y equals x, where the base raised to this gives us x. So the number I'm taking the logarithm of is a power of 10. And so the logarithm is asking a very easy question to answer. It says, what power of 10 is this number? Or 10 raised to what power is the number we're trying to log? So this 100,000 that we see here is a power of 10. And so if we start by writing 100,000 as a power of 10, we can rewrite this as the logarithm of 10 raised to the 5th power. Well, then if you answer the question, what power of 10 is 100,000, you can see the powers right here. It's 5. So the answer to this would be 5. And that's a neat trick, but I really want to focus on this log in the base 10. Base 10 logarithms and base 10 exponentials are inverse operations. In the past, we've referred to x squared and the square root as square root and square being inverse operations. And we would find that those two cancel out and leave us just the input, x. Well, base 10 exponentials and base 10 logarithms will do the same thing. If you apply a logarithm to a base 10 exponential, we'll actually see a canceling out, or the inverse operations work for us here to leave just the exponent of 5. All right, let's apply that to this bottom number here too. We have this operation here with log of 10 raised to the 5.3 power. Well, just like in this previous expression, the logarithm asks what power of 10 is this number, so we could look to the power right away. But if we think of inverse operations, the base 10 exponential and the base 10 logarithm are inverse operations, so these will cancel each other out, leaving just the exponent of 5.3. Okay? Now let's focus on this, log of 0.0001. Well, this is not a thousandth or a tenth, but it is, if we count the spaces, tenth, hundredth, thousandth, 10 thousandths. So this is actually a fraction of a 10, and so I'm going to rewrite this as a fraction of 10 first. Log of 1 over 10,000, like so. And 10,000 is a power of 10, so I could rewrite this one more time as 1 over 10 to the power of 4. Okay. Well, earlier we saw that in the logarithmic and the base 10 exponentials that the when you have a power like this on the denominator, that can be written as a negative exponent of 10. So this function rule right here, or this operation of log, allows us to take this negative exponent out. So when you take the logarithm of this number, you'll get out a negative 4. It just refers to the exponent, but the exponent would be the negative power of 10. Those are equivalent. Okay, shortcuts. Some of you look for those patterns, and I do too as a mathematician. So I look at these and I go, wait a minute. If I count the number of zeros over here in the logarithm, this is a base 10, so they're multiples of 10, and the number of zeros are 5, so the logarithm is really asking for the number of zeros that are here. Yes, that's true, but be careful. If you go over here and count the number of zeros, you would only see 3 zeros, right? Well, that's not a negative 3, it's a negative 4. So you have to be careful that the zeros show up as a multiple of 10, this being 1/10,000th, and there are actually 4 zeros as a multiple of 10 here. So we do see the zeros there. If you're looking for a shortcut that way, when you have decimal versions, you're taking log of the decimal, count the number of places. There's 1, 2, 3, 4 place values. That will help you to get out the negative 4 we need. Okay, one last problem to look at here. We have a base 10 exponential raised to the power of log of 12. So we're working with an exponential function and a base 10 logarithm. Again, these two are inverse operations. Note the reverse order from this one. This was a base 10 logarithm, and we're taking a base 10 exponential. The logarithm applies to the base 10. Well, that is no different than our square root and x squared if we write things this way. If I start with the square root of x and then square them, the inverse operation still would leave us with just x. This order, too, works here. Base 10 raised to a log cancels off, leaving just the exponent of 12. So there we see how the logarithm and base 10 exponentials work as inverse operations.